Hi, hello. Yeah, now let me start to record. Okay. Yeah. Okay. My name is Nong Yi. My research area is smart materials and devices. So I'm actually looking for the highly motivated, self-driven, and dedicated PhD candidates. So you can be in all these areas such as material science, thermal science, chemistry, physics, and machine learning. Okay. So just very quickly, I introduce what we have been doing for these past few years and our experience. And most of my job is working on the smart materials and devices, but majorly in this smart window. It's because of this data. You can say this is just US data. So 4% primary energy actually has been associated with energy consumption. So that's why we need to stop this or reduce this energy consumption in buildings. And window is the least energy efficient part. Okay. And when you do any research, right? So people are just working to keep increasing its performance, whatever like device or materials, right? So in this smart window devices, so we are aiming for enhancing this TILU and delta T so for many, many years. But the question, so what is TILU and delta T so? So basically just TILU is luminance transmission for the window, and delta T so is just heat modulation capability of a window because we want more heat in winter and less heat in summer, right? Something like this. We don't really talk about the details or very exact scientific explanation, but just let you know. So these are the three important things in this research. And we have been doing this whole area for many, many years. For example, like we work on these two materials. One is vanadium dioxide, the other one is hydrogel. And we publish so many papers on this area. But then we have this path dependence. So we call it path dependence. Just keep doing this the very organic, inorganic, and hybrid, all these things, right? And just keep increasing these three things. But the question we should ask ourselves, what are the next ones? So that's why in 2019, so I wrote this review paper for advanced energy materials. So these are the 5 categories we think we should improve in this area. So for example, the number one is consider heat transfer, multifunction design, customer design, scalability, and durability. So I just very quickly talk about a few things here. Okay, so for the first of all, like for example, like consider the heat transfer. So in my area, people only talk about just let me use this uh, pointer, right? I use this one so you can see. So in my area, people just talk about here. So basically owning until here. Okay, so people only talk about solar modulation, but actually for this region, it's also important, which is from 2.5 to 25. So there's a non-wavelength infrared range. Okay, so at the very beginning, we just use very simple ways. So we just use a flipping of the window, trying to control this region, and we can see once we introduce a new one here. So this is a new performance index. New performance index, so we can get them super high. So for example, right, so once we introduce this new performance index, data emission, so even though the conventional one, like for TILU and delta so it is not that good, so only 72 and 50, but once we introduce a new performance in, now this is 85, so the energy consumption is much improved in these different regions. Okay, so this is our very first paper. So then we continue work on it. So we keep increasing this. So you can see the conventional one. So we only modulates until 2.5 micron. This near infrared range, but we don't modulate anything in this long wavelength infrared. But we're only spin coating a very similar PMMA as a spacer. So this is spacer from this fiber parrot resonator. So we can just modulate. You can see modulate this this is summer, this is winter, in this long wavelength infrared. So we can just immediately increase this energy consumption. So it's a very simple experiment, very simple design. So compare with the static no-E commercial window, so we can just increase the energy saving across all zones globally, from zone 1 to zone 7 globally. Okay, so this is a very simple way of a very simple design and a very simple way to enhance the energy saving performance. So then we further on consider the heat mass. So for example, because people never think about if we use a double glaze window, right? But like for water is actually intrinsically has very high heat capacity, right? So we just introduce a very thin, with very layer, the encapsulated the liquid, a small responsive liquid in this window panel. So you can see, so we have this big, once become a liquid, so it's very uniform. So and very easy to get large scaled. So you can see, once we introduce this one, so we can just reduce the energy consumption. And the most important thing, we are going to have this peak shifting due to this very large heat capacity coming from the liquid here, because we are using hydrogel. So it's not hydrogel anymore, it's hydroliquid. So hydroliquid have 90%, so which are water. So we use this naturally very high heat capacity of water in this encapsulated window. And moving on, so compare with the radiation. So there is another one, which is evaporative cooling. So evaporative cooling actually is more effective compared with radiant cooling. So we collaborate with the CAS and just trying to make the hydrogel with a very large pores, controlled pores, and sprayed on top of this the large scale production. So we have a very good coupled evaporative cooling and radiant cooling, and give much enhanced cooling effects. You can see, so that people have done, the students have done this comparison. So PVDF is one of the best really cooling materials. But once we introduce evaporative cooling, so you can see we can further enhance this cooling effects of more than 10 degrees. So that's really a huge thing here. And continue, we also work on this modulate evaporative cooling. And so for this previous work, we only talk about cooling, right? But in 4 season regions, we not only need the cooling, but also you need warming in winter. So that's what we have done. We just use a very simple design. So make it, for example, this is summer. So we have this top layer is going to open up. So you're going to have high emission and high evaporative cooling, right? And also during the summer, so we just close it during the winter. So we just close it. So become a heating mode. So this one have a low E and also suppressed evaporative cooling. Okay, so this is so you can see this work. So we have a very large evaporative cooling modulation and large modulation in solar transmission, and also the solar modulation, the emission modulation. Okay, so this is our very latest paper. So it's a very simple concept. And further on, so we have also another one. So you can see, again, we just use same concept, but have a little bit difference in the design. So this is a maxing layer. So when the temperature goes up, so this maxing layer is going to sort of like sink down. So we are going to have very high, strong water evaporation and very high sunlight refraction. Okay, so this is a summer state. Once it becomes winter, so this hydrogel is become very we have this hydrogen bonding, HPC bonding, right, encapsulated. So this one you can see we are going to have a very weak water evaporation and high sunlight transmission. Okay. So I just ignore the details here. And multifunction, this is second category, multifunction design. So previously, for example, people dealing with solar cell, right? They only talk about this region, right? They just keep enhancing the PCE. So we design a cross multi-spectrum, for example, from 0.3 from UV to 25 microns from long wavelength infrared. So you can see we use this region, so the visible region to do the energy generation. Near infrared, from near infrared, we have this energy modulation. So this is winter, this is summer. And from 2.5 to 25, this long wavelength infrared, we have a low E coating to make the insulation. So this is the first multi-spectrum design. So, and I ignore the details. We put vanadium dioxide here. So you can see by doing so, we can not only enhance the PCE, and also we are going to have the heat modulation. Yeah, so these are some simulations here. This is our new design. So in this design, we are not only have energy saving, which is use electrochromic design to realize the energy saving, but this electrochromic devices at the same time it is also a energy storage like a batteries. So once it become batteries, you can use in the nighttime, right, as a battery, and so that's why this is standalone energy efficient window. And also we have this as a solar cell. So this is solar cell. So the solar cell is used to collect and harvest the sunlight during the daytime. So this is 3-in-1 devices. And this is another one. It's more for defense people. So people are in defense. They need immediate invisible state. So example, like the B3, right? So for this state, we just use a very small force. So just press it. So it's going to give you the immediate invisible state. Okay, so it's a very simple design here. And so we just wrote this review paper again, just let the community know. So besides video cooling, so which is for this yellow region, video cooling, and we also need radio warming in this blue region, which is high latitude regions, and for the relative like a modulated state, so which is in this green region. Okay. So this is the very first one, which we call the radio warming class. So once you need radio warming, right? So you need very high solar transmission and very low emission here. So by doing so simply we just use dopant, control the electron number density. So we're going to increase the electron mobility. So we are going to achieve this very good performance radio warming glass. So you can say this is near ideal materials. Okay. Yeah. And this is another one. So this is boron nitride coatings. So boron nitride is a very durable ceramic glass window. So by simply doped a little bit carbon inside the boron nitride, so we're going to reduce this emission here. So this is another radio warming carbon doped nitride coatings. Okay. Yeah, I just skipped the details here. And also we need to think about in high latitude regions. So for the summer and winter, they're going to have a different sunlight, right? So instant angles. So this is a new factors we need to consider. Just have a different instant angle. So we give them this tilted and the metal surface, the structures here. So you can see, use a mesh printing. And also we need to think about durability. So for example, we used to deal with a lot of materials such as vanadium dioxide and hydrogel, but unfortunately, these materials are quite fragile. So we need to keep looking for new materials. So in this paper, so we have used this PDMS and with this PEO and composite phase change materials. So by modulating, so you can also achieve this large modulating as hydrogel, but much improve the environmental durabilities here. And we also, in this new review paper, so we just let the community know. So there's so many things we need to do. Like, for example, we need looking for new materials, consider the cost and durability. As a material scientist, so we're always looking for better materials, much more durable materials. And when you think about thermal insulating and using use the waste thermal electric generation, and also think about evaporative cooling and angle modulation. And so you can see we need to keep just not only talking about video cooling, but also modulation and warming, and expand application scenarios like greenhouse, vehicle, solar cell, and also the outer space, right? So there's so many things we can do. So I just quickly, and also we need to use how to say, the machine learning here, right? So you can say I just give you the one thing here. So our latest work, so machine learning aided design. So that's why I also need students with good experience with machine learning. So in this paper, because like for material scientists, so we're always struggling with different process parameters. In this paper, we talk about, because in this design, we need to consider this vanadium dioxide particle size and the spacer, the fibroparate structure space thickness. So we use FDTT to simulate and trying to understand which factors is important here. So you can see in this one, so we know, so if you want to modulate there's long non-wavelength infrarange, so vanadium dioxide particle size need to be very, very small, right? So this is from the FTTT simulation and machine learning. So you can say this. So this is we use a database establish the forward prediction, then on-demand inverse design. Okay, so then we use a validation and experiment. This is a full process, and of trying to understand which parameters is important to keep increasing the performance. So this is the one we have used. Okay, so you can see here. So we need to have very small particle size of vanadium dioxide, right? For example, here this is for the long wavelength infrared, and this is for the TSO, which is from 2.5 from 2.5 to 2.5 so region. That's all. Okay, so both need very small vanadium dioxide particles. Okay, but for the spacer, right? So then you need there's an optimal range. Okay, so by using this conclusion, so we trying to fabricate very, very small nanoparticles. So you can say once we have this very, very small nanoparticles, so we're going to get enhanced delta TSO, which is from 0.25 to 25, and also we're going to have enhanced delta emission, which is from non-wavelength infrared. Okay, so this is the first machine learning aided design. And also this is a little bit more complicated because my science paper only talk about the window, right, which is facing outdoor. Okay, so which we only talk about if your glass the coating is putting on the outside, which is need facing your door, but the outdoor. But the problem is that this one is going to have a very poor visibility, right? Because you need to have wind and UV, very high UV. So, and raindrop, all this put very high stress on the materials. So then we think we need to put inside, like propose double gauge glass. But double gauge glass, right, if we put it here, so this will cause phase 2. So we don't know what is the optical properties needed, right? So that's why you use machine learning. We need to understand what is solar transmission, solar reflection, and the long wavelength emissivity. And with so many weather data, such as wind speed, precipitation, elevation. There's so many things here, okay? And so complicated and in different regions. So that's why we use machine learning, trying to understand what is the best optical properties we need if the the phase two here, which is phase two here. Okay, so then by collaborating with Professor Li Hongsheng, so we have built several models, model one, model two. So we come out that if the coatings inside this phase two, right? So we basically need very high modulated. So this is a winter, still winter, you need high TSO, but summer you need low TSO. But for the long wavelength infrared, which is from the 2.5 to 25 here, so you actually need low E. Okay, so that is our conclusions here. So we use this machine learning to help us to get this conclusion. Okay, and also they analyze, let us know that if for the tropical weather, right, TSO actually is more important, but in the winter season, actually emission is more important. So this is very good way let us understand how different the weightage of different wavelengths is going to influence the energy performance. And so I stop here. So we also fabricate a few smart materials by using this thermochromic one, but on top we give them a low emission, right? No emission coatings. So by doing so, and also there's a lot of simulation here, and we prove that such design is going to get much better enhanced energy saving here. Okay, so you can see this is a few tests here. So if we compare with the clear glass and commercial single glazed low E glass and commercial double glazed low E glass, so our coating is going to, our devices is going to achieve overall from zone 1 to zone 8 overall energy saving across globally. Okay, so it's just very quick introduction of our recent research in my group. So there are certain like take-home points. So you can say this is highly interdisciplinary work, and also we are keep just looking for new things here. Yeah. So thank you very much. So please contact me. Thank you. Oh, yeah. One last thing is I have two quotas, so even you cannot secure Hong Kong PSF, but I can still give you the position with scholarship. Thank you.